In this presentation, I will show you how to find the energy emitted and absorbed when electrons change energy levels. I will also show you how to use your reference table to find how much energy is needed to remove an electron from any energy level in hydrogen or mercury. When electrons absorb energy, they release that energy in the form of light. Each element is capable of only absorbing or emitting a particular set of energies or colors. If you send the full spectrum of colors at every element on the periodic table, each element would absorb a unique set of colors. The physicist Niels Bohr explained that this unusual set of observations could only be explained if electrons were limited in the energies that they could possess. In this presentation, I will focus mainly on the different kinds of questions related to the Bohr model. In the Bohr model of the atom, the electrons orbit around the nucleus like planets around the sun, but unlike planets orbiting a body, electrons were restricted in the energies that they could possess. The electrons could only absorb an energy that could get them exactly to the next permitted energy level. If an atom is sent a photon whose energy is not the difference between two possible energy levels, that photon would simply pass through the atom without being absorbed. Here are the important things to remember about the Bohr model of the atom. Permitted orbits of an electron in an atom are limited. Each orbit is a different energy. Inside orbits have lower energies than outside ones. When electrons in an atom change energy states, they absorb or release energy. When electrons go up in energy level, energy is absorbed. When they go down in energy level, energy is released. Up, absorb, down, emit. Once again, that's up, absorb, down, emit. These two charts found on your reference table show the energies that are possible for an electron in a hydrogen and mercury atom. You can see that exactly 10.2 electron volts must be absorbed for an electron in hydrogen to go from the first to the second energy level. This number represents the difference between the absolute value of these two energy levels. If you are asked about the energy level changes for mercury, you use the chart on the right. If an electron moves from the H level to the B level, it emits a photon with an energy equal to the difference between the absolute values of these two levels. We know the energy is emitted because the electron is moving down in energy level. Remember, up, absorb, down, emit. Hydrogen in the unexcited state contains a single electron in the first energy level. When hydrogen absorbs a photon of energy with the correct amount, it is considered to be in the excited state. The correct amount of energy is one that is equal to the difference between the energy level of the first level and any other allowable energy level. The electrons can only absorb or emit energy that is equal to the difference between the absolute value of any two energy levels. A single photon of energy is given off when electrons go down in energy level. The energy level at n equals 2 is 3.4 electron volts, and the energy level at n equals 5 is 0.54 electron volts. To find the energy given off, we simply remove the negatives from the numbers and subtract. How much energy is needed for an electron in the n equals 1 energy level to move to the n equals 2 level? When we subtract the energy at the first and second level, we get 10.2 electron volts. In order to find the frequency of this photon, we need to use E equals hf. H is Planck's constant, which is found on page 1 of your reference table. We can't use this equation until we convert electron volts into joules. On page 1 of your reference table, we see that 1 electron volt is 1.6 times 10 to the negative 19th joules. After we convert, we see that the energy of the photon is 1.6 times 10 to the negative 18th joules. After we plug into the equation, we get a frequency of 2.4 times 10 to the 15th hertz. Which energy level transition in mercury will produce a photon emission of 0.22 electron volts? In order to find out which energy level transition produced this photon, we need to find two energy levels that have a difference of 0.22 electron volts. If you look at level C and B, they do have a difference of 0.22 electron volts. The two charts on your reference table can also tell you how much energy is needed to remove an electron from any energy level. All you need to do to remove an electron at any energy level is to give that electron an energy that's greater than or equal to the energy at that level. So since the energy of an electron on the n equals 1 level of hydrogen is 13.6 electron volts, then you need 13.6 electron volts or greater to remove that electron from the atom. To remove an electron from the n equals 2 level, you need 3.4 electron volts or more. A photon having an energy of 15.5 electron volts is incident upon a hydrogen atom in the ground state. The photon may be absorbed by the atom, and since the energy of the photon is greater than the energy of the electron at the ground state, the electron will be ionized and leave the atom. And this is the end of my presentation on solving problems with the Bohr model of the atom.